Slope-Deflection Equations derivation. This is a continuation of lecture SA 27, in which we introduced and illustrated the slope deflection method for beam analysis, but left the derivation of the slope deflection equations for a later time, a task that we are going to take up in this lecture. Imagine a continuous beam having multiple segments. A typical beam segment could be subjected to external loads, like segments AB and CD, or it could be external load free, like segment BC. Let's consider each case separately. First, we examine the simpler case, where there are no external loads placed on the segment. Although such a segment is not directly subjected to any loads, it does deform and carries internal forces. For example, the concave up deflection of segment BC means the member carries a counterclockwise moment at B and a clockwise moment at C. Generally speaking, a typical beam segment has a bending moment at its left end and a bending moment at its right end. If the ends are labeled B and C, we refer to these moments as MBC and MCB respectively. Further, we denote the beam's rotation at B as theta B and use theta C for rotation at NC. The slope deflection equations define the mathematical relationship between these rotations and bending moments. More specifically, there are two slope deflection equations for the segment. One equation for defining MBC in terms of rotations, theta B and theta C, and another equation for defining MCB in a similar manner. Before we start developing the slope deflection equations, let's pick a sign convention for member end moments and rotations. I'm going to use counterclockwise direction as positive. So I'm going to place MBC like this, causing a positive counterclockwise rotation at B. Similarly, we get a positive rotation at C when MCB is placed in the positive direction. This means the entire beam segment is assumed to deflect like this. Now we are ready to get to the essence of this lecture, defining member end moments in terms of end rotations. Consider a simply supported beam subjected to a positive moment at A, like this. I'm going to label the moment MAB. The beam is going to deflect upward. This means end A rotates counterclockwise, but end B rotates clockwise. Let's refer to the rotation at A as theta A1 and call the rotation at B theta B1. We can easily determine these joint rotations in terms of MAB using the virtual work method. The step-by-step details of these computations are presented elsewhere. Here I'm going to give the results only. Theta A1 equals MAB L over 3EI, and theta B1 equals MAB L over 6EI. Where L is the beam's length, E is modulus of elasticity of the material, and I is the beam's moment of inertia about the axis of bending. Let's examine the beam one more time, but this time place the positive counterclockwise moment at B like this. I'm going to refer to this bending moment as MBA. The beam is going to deflect downward like this. I am going to denote the end rotations as theta A2 and theta B2. Similar to the first loading case, we can determine the two end rotations in terms of MBA using the virtual work method. Here are the expressions for theta B2 and theta A2. Okay, now what do we get if we superimpose these two diagrams? We get this diagram, where this rotation can be written as theta A1 minus theta A2, and this rotation can be written as theta B2 minus theta B1. Or let's refer to this overall rotation as theta A and call this one theta B. So we can write, and Here we have two equations in terms of the member end moments and rotations. Let's treat MAB and MBA as unknowns and write them in terms of theta A and theta B. To do so, first rearrange the equations like this. Summing these equations gives us, or substituting this for MBA in one of these equations, we get Finally, here are the slope-deflection equations for a beam segment that is not subjected to any external loads. These equations follow our sign convention as the rotations and moments are shown in the positive, counterclockwise direction in this diagram. We also need to talk about the case in which the beam segment is subjected to external loads. How would such loads affect the slope-deflection equations? Before we delve into that discussion, let's spend time analyzing a few simple, indeterminate beams to better digest what we have learned so far. Consider the following indeterminate beam. It is subjected to a concentrated moment at the left end. We start by isolating the joints of the structure. Here, we have two joints and one beam segment. So we get We denote the joint rotations as theta A and theta B, and refer to the end moments as MAB and MBA. The slope-deflection equations for segment AB can be written as Since the member end moments also appear at the joints, we get Note the at B, in addition to MBA, we have an unknown moment reaction labeled MB. Therefore, joint equilibrium equations become Substituting this expression for MAB and this expression for MBA in the equilibrium equations, we get Here we have two equations but seemingly three unknowns, right? So how do we solve for MB, theta A, and theta B using only two equations? A close examination of the problem, however, reveals that the equations contain only two unknowns. We actually know the numeric value for theta B. It is 0. Why? Because the right end of the beam is fixed, meaning there is no rotation at joint B. This allows us to rewrite the equilibrium equations as Solving these for the unknowns, we get Substituting 25 over EI for theta A and 0 for theta B in the slope-deflection equations, we get Now that we have determined the member end moments, we can easily calculate member end shear forces. Here is the complete free body diagram for segment AB. So we can write Solving these equilibrium equations for the unknown shear forces, we get Now transfer these forces to the joints and determine the vertical support reactions. Here is the analysis results. We will discuss the formulation of slope-deflection equations for the case of externally loaded members in the next lecture. For now, see if you can analyze the following beams using what we have learned so far.